In Episode 9, titled Confidence Intervals, Interpretation, Width, and Common Traps, the focus is on using intervals to speak uncertainty clearly, because DataX rewards professionals who can communicate what the data supports without pretending to have perfect certainty. A single-point estimate is easy to say, but it often hides the most important question, which is how much that estimate could plausibly vary if you had collected a different sample. Confidence intervals are one of the cleanest ways to make uncertainty visible without turning every decision into a debate about statistics. On an exam, confidence intervals appear as an interpretation challenge because the math is usually secondary to the meaning and the implications. If you can interpret an interval correctly, reason about what makes it wider or narrower, and avoid the common traps, you will pick the best answer more reliably. This episode is about turning intervals into a practical decision tool rather than a confusing artifact of formulas. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The most useful way to interpret a confidence interval is as a plausible range of values for a population parameter given your sample and the method you used. The parameter might be a population mean, a population proportion, or a difference between groups, and the interval is your way of expressing what the data supports as reasonable. It is not claiming that every value in the range is equally likely, and it is not claiming that values outside the range are impossible. Instead, it is telling you that, under the assumptions of the method, this range is the one your procedure would produce in a large proportion of repeated samples at the chosen confidence level. In practical speech, you can think of it as the set of parameter values that are consistent with the observed data and the method's assumptions. The exam often tests whether you can keep the focus on the parameter, not the sample, because that distinction is where many interpretations go off the rails. One of the most common traps is claiming a probability that the parameter sits inside a specific interval, and the exam expects you to avoid that phrasing. In the frequentist interpretation, the parameter is fixed and the interval is random because it would change if you took a different sample. The confidence level describes the long-run behavior of the method, meaning that if you repeated the sampling and interval construction many times, a certain proportion of those intervals would contain the true parameter. Once you have computed an interval from your sample, it either contains the true parameter or it does not, and the confidence level does not assign a probability to that specific interval after the fact. This is subtle, but the exam uses it because it separates correct conceptual understanding from casual, incorrect language. A safe approach is to say the interval provides a plausible range for the parameter under the method, rather than saying there is a certain % chance the parameter is inside it. Interval width is not random noise, and the exam often tests whether you understand what drives it, because width directly influences decision confidence. Variability is a major driver, because more variability in the data leads to more uncertainty about the parameter, and therefore wider intervals. The chosen confidence level is also a driver, because higher confidence generally requires a wider interval to capture the parameter more often across repeated samples. Sample size is another driver, because larger samples typically reduce uncertainty and produce narrower intervals, assuming sampling is representative and measurement is sound. These drivers interact, meaning you can have a large sample but still get a wide interval if variability is high, or you can have low variability but still get a wide interval if the sample is tiny. On the exam, you will often be asked what action would narrow the interval, and the best answer typically involves increasing sample size or reducing variability through better measurement or better design. When you can connect with to these drivers, you can reason through interval questions without relying on memorized formulas. Narrower intervals are more precise, not necessarily more accurate, and that distinction matters because learners often treat narrowness as proof of truth. Precision means your estimate is tightly bounded, suggesting low uncertainty about the parameter given the method and the data. Accuracy means closeness to the true parameter value, and you can have a very precise interval centered around a biased estimate if your sampling or measurement is flawed. A narrow interval around the wrong answer is still wrong, and the exam can hint at this through scenarios involving selection bias, measurement bias, or unrepresentative samples. This is why it is not enough to chase narrowness. You must also ensure that the data collection process supports unbiased inference. In professional terms, precision tells you how tightly you can speak, but accuracy tells you whether you are speaking about the right thing. DataX rewards learners who can explain that difference because it signals mature reasoning about uncertainty and data integrity. Choosing a confidence level is a policy choice that should be based on decision risk tolerance, and the exam often frames this through consequences rather than through mathematics. A higher confidence level means you want to be more cautious about excluding the true parameter, which can be appropriate when the cost of being wrong is high. A lower confidence level means you accept more risk of missing the true parameter in exchange for a narrower interval, which might be acceptable for exploratory analysis or low-stakes decisions. The key is that confidence level is not a moral virtue. It is a knob that balances caution and precision. In a safety-critical context, stakeholders may prefer high confidence because they want decisions supported by stronger evidence. In a fast-moving business context, stakeholders may accept lower confidence if decisions must be made quickly and can be corrected later. The exam rewards answers that tie confidence level to consequences and stakeholder needs rather than treating it as a universal standard. Another exam trap is the idea that overlapping confidence intervals prove there is no difference between groups, and that is not a valid conclusion in general. Overlap can occur even when a difference is statistically significant, and non-overlap can occur in ways that do not align neatly with formal tests unless specific conditions hold. The right approach is to avoid using overlap as a simplistic decision rule and instead consider the interval for the difference itself or use appropriate hypothesis testing logic. The exam may present two group intervals and ask what you can conclude, and the correct answer often acknowledges that overlap alone does not settle the question. What matters is whether the data supports a meaningful difference relative to uncertainty, and that requires either a direct interval for the difference or a test designed for that comparison. This is a classic example of why DataX rewards careful interpretation, because casual heuristics can lead to confident but incorrect conclusions. If you treat overlap as suggestive but not decisive, you will stay aligned with correct reasoning. Confidence intervals become especially useful when you read their endpoints as business impact boundaries rather than as abstract numbers. If an interval describes a change in conversion rate, error rate, or time savings, the endpoints represent plausible best-case and worst-case outcomes under the assumptions. Decision-makers often care less about the middle point than about whether the worst-case outcome is still acceptable or whether the best-case outcome justifies the effort. On the exam, you may be asked to interpret an interval in terms of whether it supports a decision, and the best answer often involves recognizing what the endpoints imply for impact. For example, if the entire interval falls above a minimum meaningful improvement threshold, the decision is easier than if the interval straddles that threshold. This is not about overpromising. It is about using uncertainty to set realistic expectations and avoid surprise. When you practice reading endpoints as boundaries, you train yourself to connect statistical output to practical decision language. Misinterpretations also arise when learners confuse sample values with parameters, and the exam expects you to keep those levels separate. A sample mean is a statistic computed from observed data, and a population mean is a parameter describing the full population you care about. Confidence intervals are typically constructed to estimate parameters, not to describe where future individual observations will fall, which is a different kind of interval. If the question is about the population parameter, the interval is about that parameter, and you should not describe it as though it is describing individual outcomes. The exam may tempt you with language that blurs these ideas, especially in scenarios where the sample seems large or where the dataset is described casually as all the data. If you catch yourself speaking about a sample statistic as though it were the population truth, that is your cue to slow down and restate the population and sample explicitly. Keeping the parameter focus intact is one of the surest ways to avoid wrong answers in interval questions. Confidence intervals connect to hypothesis tests through inclusion logic, and the exam often tests that relationship because it is a clean bridge between two concepts. For a two-sided test at a given alpha, a confidence interval at the corresponding confidence level can be used to infer whether the null value is plausible. If the interval for a difference excludes 0, that often corresponds to rejecting a null hypothesis of zero difference at the matching significance level. If the interval includes 0, that often corresponds to failing to reject the null under the same mapping, though interpretation still requires caution about power and practical importance. The key is that the interval provides a range of plausible parameter values, and the null value being inside or outside that range informs whether the null is compatible with the data under the method. This relationship can help you sanity check results without doing extra computation, which is useful under exam time pressure. DataX rewards the learner who sees intervals and tests as consistent tools rather than disconnected topics. There are scenarios where assumptions feel questionable, and in those cases, the exam may reward awareness of bootstrap intervals as a practical alternative. Bootstrapping is a resampling approach that uses the observed sample to simulate many pseudo-samples, allowing you to approximate the distribution of an estimator without relying as heavily on strict parametric assumptions. Conceptually, it is a way to build an interval when the usual formulas may be unreliable due to complex distributions, small samples, or unclear conditions. The exam is not typically asking you to implement a bootstrap, but it may ask what approach is appropriate when distribution assumptions are not trustworthy. Recognizing that robust or resampling-based intervals exist shows that you understand that methods have conditions and that you can choose alternatives when conditions are weak. This fits the DataX emphasis on judgment, because you are selecting an approach that matches uncertainty rather than forcing a method that does not fit. When you see scenario language about non-normality, heavy skew, or unclear distribution behavior, bootstrap thinking can be the clue that the exam is testing method selection under imperfect assumptions. Skewed data is another reason robust methods matter, because skew can distort naive interval construction and naive summary measures. When distributions are heavily skewed, intervals based on normal approximations can be misleading, especially with smaller samples or strong outliers. In these cases, robust summaries and robust interval methods can provide more reliable guidance because they are less sensitive to extreme values and assumption violations. The exam may describe data like response times, transaction amounts, or counts, all of which commonly exhibit skew and outliers. A correct answer in such scenarios often involves choosing approaches that respect the data behavior, such as using medians, transformations, or robust interval methods rather than forcing mean-based assumptions without validation. The point is not to memorize a catalog of techniques, but to recognize that data shape influences what reasonable uncertainty looks like. When you connect skew to method choice, you will select answers that reflect professional caution and sound inference.
A simple anchor that keeps interval thinking clean is to remember that precision equals width and confidence equals caution, and to treat those as distinct ideas.
Precision is about how narrow the interval is, meaning how tightly you can bound the parameter estimate given your data and method.
Confidence is about how cautious the method is in capturing the true parameter across repeated samples, which often widens the interval when you demand higher confidence. If you mix these ideas, you can end up saying incorrect things, like assuming higher confidence means higher precision, when it usually means the opposite. The anchor also helps you reason about trade-offs, because you can ask whether the scenario demands caution or whether it demands tighter bounds for decision-making. When you understand that confidence and width trade off, you can explain why an interval changed when sample size or confidence level changed, which is a common exam pattern. This anchor keeps your language consistent and your interpretations defensible under pressure.
To conclude Episode 9, state one confidence interval correctly and then explain its meaning in plain language that respects uncertainty and avoids the common traps. You want to be able to say that the interval provides a plausible range for a population parameter under the method's assumptions, and that wider intervals imply less precision while narrower intervals imply more precision. You also want to be able to say what drove the width, such as variability, confidence level, and sample size, and what the endpoints mean for decision impact. Avoid saying, "There is a certain % chance the parameter is inside the interval," and instead speak in terms of the method's long-run behavior and plausibility. Then connect the interval to a decision by explaining whether the plausible range includes outcomes that are acceptable or unacceptable for the stated goal. If you can do that smoothly, you will be able to handle most DataX interval questions with calm, disciplined reasoning rather than guesswork. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.